Hi, hello. Okay, so today we're going to talk about sets. Sets are natural to come early in the course because they form the theoretical foundation of all of mathematics, so it's natural to put them first. They are really kind of the language in which we describe all the other ideas. Okay, so a set is a collection of things. I imagine that most of this material is familiar to folks on some level, but just to give everybody the same vocabulary. A set is a collection of things. Those things are called elements. We won't have much to do with a collection of elephants or a collection of you know, circus clowns. Or we're going to work with collections of numbers typically. So those things are called elements. We denote a set with curly braces where you put the elements in between or else where you describe the elements. So sometimes for small sets you put the elements in between, but often you'll give it some kind of description. This is called set builder notation. It'll say the set of X such that, you see the vertical bar, you read out loud as such that. And again, I'm assuming that most of this is familiar to everybody. Sometimes one person has not heard one thing and one person has not heard another. So the set of X such that X is prime and X is less than 6. And of course, these two sets are the same set. Two sets are equal if and only if they contain the same elements. So if you collect together a bunch of stuff and two people collect the same stuff, why they have the same set. There are some consequences to that definition. Seems like a straightforward definition. There are some consequences. In particular, the collection consisting of a 2, a 5, a 3, and a 2 is the same as the collection consisting of a 2, a 3, and a 5. That is to say, in a set, order doesn't matter, and repeats collapse. This has a pair of 2's. This has a single 2. Doesn't matter. Same collection. To denote the is an element of, we write the symbol epsilon there, kind of a funny looking epsilon. For example, 3 is, we read that aloud as is an element of. 3 is an element of 2, 3, 5. 4 is not an element of 2, 3, 5. Just to help a person with how do you write that by hand, I'll write down my personal, what I would write, even though I have terrible handwriting. So 3 is an element of 2, 3, 5. And 4 is not an element of 2, 3, 5. Okay? Went the wrong way. There we go. We often name sets with uppercase letters. It's good to have a convention, and the uppercase letter convention works because then you can denote the elements with the associated lowercase letters. So you could write the set capital A as 325, and then you could say little a is 3, and little a is an element of capital A. That all works. It's relatively easy to understand what's happening. Here are some common sets that you run across all the time on the interwebs. The natural numbers, see how it has a double line in it there? The integers, the positive integers, the rational numbers are the fractions, p over q, where q is not 0. The real numbers, meaning both rational and irrational, and the complex numbers. Just to give you again a handwriting example of what's happening here. So my handwriting for any of these would be the natural numbers, the integers, the rationals, the reals, and the complexes. Okay? In computer science, you often deal with characters such as A or B. A set of characters is called an alphabet and usually denoted with the letter capital sigma. The set of strings over that alphabet, capital sigma star, that's called the Kleene star. Anyway, a set of strings over that alphabet, capital sigma star, contains all finite length sequence of characters from sigma. So if sigma is the lowercase routine ASCII letters, then some elements of sigma star are the string DOG, XTTY, or don't forget the empty string, the string that has no characters in it at all, and we often denote that with a, what happened? Oh, there we go. Often denote that with a lowercase Greek letter epsilon. Sometimes people from Germany use a lambda, but anyway, we're going to use a lowercase Greek letter epsilon. Okay, and again, I think most of this stuff is familiar to a person, but maybe, for example, empty string is new to you. That's why we're going through some things that you know already, but some things maybe that some people do not. If S and T are sets, then the first one is called a subset of the second if every element of S is an element of T. You write it this way with this symbol here. You would read that out loud as S is a subset of or maybe equal to T. So if, for example, S is 2, 4, 6 and T is 1 up to 10, then S is a subset of T. You sometimes say T is a superset of S, not as often. I don't know, sometimes you say it, but might be 90-10 or even 95-5% of the time. If S is 2, 4, 6 and T is 1 through 10, then S is a subset of T. And because S is a subset of T but not equal to it, we say that it's a strict or a proper subset of T. We may write S subset, see the difference? There's no underbar. Or we may emphasize the fact that it's unequal by writing the underbar with a slash through it. I have to caution you, you sometimes run across authors that write this for what we are writing here. I don't know what to tell you. I think those folks are doing it wrong, but they think I'm doing it wrong. I do think this is more common these days, but you do sometimes see this. So another example is that the natural numbers are a subset of the integers. The prime numbers are a subset of the natural numbers, which in turn are a subset of the integers. Okay, and again, I think this is familiar to folks, but there may be a thing or two where a person says, I've never seen that one before. Union, intersection. So if you have two sets A and B, it's common to draw a picture where you might have, for example, inside of the box will be all the numbers. Inside the circle A is all the even numbers. Inside the circle B is all the multiples of 5. And the union of even numbers and multiples of 5 is you color both circles, including the overlap. So that's the union of, in my example, the even numbers and the multiples of 5. Okay, that's the union. Intersection is the overlap. If I have, again, this is all the numbers, that's called the universe. Inside the universe is all the natural numbers. Inside A is all the even natural numbers, and inside B is all the multiples of 5. Why then the intersection would be things that are multiples of 5 and also even. That is to say, they're multiples of 10. And the complement. So you often see complement written with a superscript C. You also often see complement written with a bar, A bar. So if A is all the even numbers, then outside it would be all the odd numbers. So shaded there are the odd numbers. It's called a Venn diagram after the person who invented it, made it popular. A caution about that third one. A lot of times when a person sees this, for example, in high school, we don't pay much attention to the universe, to the box that's around the circles, pay more attention to the circles. But in fact, with the third one, you got to be a little careful about the box. If somebody says, consider the complement of the set of all x's where x squared is greater than 2, you don't mean to include, you do not mean to include, I don't know, Hong Kong. Is Hong Kong have the property that Hong Kong squared is greater than 2? No. So you don't mean to include Hong Kong. You don't mean to include elephants. You don't mean to include all kinds of things. So that is to say, really, if you want to talk about complement, you're really, to be sensible at all, you have to describe complement in what context. What's your domain of discourse? What's your universe? Complement with respect to what? It's a small point, but an important one. So we'll sometimes write the complement, sometimes write the domain of discourse with a capital omega. That comes from some philosophical tradition of saying omega is the end of the Greek alphabet, so it's everything. Anyway, so we'll sometimes write the domain of discourse as a capital omega, sometimes a script letter U, but more often a capital omega. And so the complement is the set of all x's in omega where x is not in A. Okay, again, taking advantage of the fact that folks have seen usually most of these to sneak in a couple of fine points. Yeah, a couple of other operations. Set difference, A take away B. So it's everything that's in A but not in B. So if A is the even numbers and B is the multiples of 5, then A take away B is the even numbers that are not multiples of 10. The even numbers that are not multiples of 5 are the even numbers that are not multiples of 10. The symmetric difference is the set of things that are in A but not B, or B but not A. So here I've shaded A but not B, and also shaded B but not A, but did not shade the overlap. That's called the symmetric difference. We've already seen subset and set equality, but just to have written them all so that I have the tables in that form. A is a subset of B when X is an element of A implies that X is an element of B. And two sets are equal when X is an element of A if and only if X is an element of B. So that makes a nice match for what else is on the slide. Okay, again, going through some material that I expect most of it is familiar to a person, and sometimes taking the opportunity to sneak in a comment or two about it. The empty set. The empty set is a set that doesn't have any members. You can write it as these curly braces with nothing in between, that's fine. You can also write it as a circle with a line through it, and again, I'll do with the handwriting here. So the empty set, I will write that either this way or this way. Sometimes I forget and write it one way or the other, but anyway, one of those two ways, by handwriting, you often see it written. So I sometimes get the question, actually often get the question, how can you be a collection but not contain anything? That's not any kind of collection. Well, but I think it is. If I look at the set of people in our room who are left-handed, that's a perfectly legitimate collection. If I look at the set of people in our room who have red hair, that's a perfectly legitimate collection. If I look at the intersection of those two, what do you mean it does no such thing? I think it's a perfectly sensible concept. The set of people in the room who are left-handed and have red hair. It may happen to be an empty collection, but it's perfectly sensible to talk about that collection. A less kind of fanciful example is if I look at the set of x's which satisfy this property, the set of integer x's that satisfy this property, that's a perfectly good collection. It might not have any x's in it, but it's a perfectly good collection. So it's perfectly sensible to talk about a collection and find out it has no members. That could easily happen. For any set, the empty set is a subset. Furthermore, the empty set is unique. If I have an empty set and you have an empty set, the two of them are equal because they contain the same members, namely no members. If two sets have an empty intersection, we call the two sets disjoint. So just a vocabulary word, but disjoint, meaning they have no overlap. So here's a picture I found on the internet. The attractions between Springfield, Illinois and Maryville, Kansas, apparently is the empty set of attractions, roadside attractions. Okay, cardinality. Cardinality of a set is the number of elements that it contains. We'll talk more about cardinality, but at the moment we're just going with just a vocabulary. So the set capital A is 2, 3, 5 has cardinality 3. You write that like without absolute value bars. In general, we use absolute value bars to indicate sort of size of something. So the size of the set capital A is 3. The empty set has cardinality 0. Nothing wrong with that. The Cartesian product, again, something that we'll usually folks have seen before. Of course, folks have seen before, but just to establish the vocabulary here. The Cartesian product of two sets is the set of ordered pairs where the first element comes from the first set and the second element comes from the second set. So it's a set of ABs where A comes from A and B comes from B. If you have, for example, 2, 3, 5, and you want to take the Cartesian product with 0, 1, then you get all the pairs that begin with a 2, all the pairs that begin with a 3, and all the pairs that begin with a 5. Just as a comment, note that C cross D, you read that out loud as C cross D, not C times D. Note that C cross D is not equal to D cross C. In particular, the things that are in D cross C would begin with 0s or 1s. There is nothing here that begins with a 0 or 1. Okay, again, trying to sneak a couple comments into stuff that I think is familiar to folks. Often when we take a Cartesian product, the two sets are the same set, and the typical example is the Cartesian plane. So you do an awful lot of calculus 1, for example, by writing things in the plane, and you write that, the notation there would be you'd write r squared. Remember, r is a set of real numbers, so that you put down an x-axis, you put down a y-axis, you're looking at the ordered pairs, where x is an element of r and y is an element of r. That's the Cartesian product with two equal sets. If A and B are finite sets, then the number of things in the set A cross B is the number of things in the set A times the number of things in the set B. The cardinality of A cross B is the cardinality of A times the cardinality of B. And here's an example. It's not a hard idea, but just to go through an example, if there are 3 things in C and 2 things in D, then there should be 6 things in the cross product. That explains the time sign. Same thing works for triples or 4 tuples, or we won't have many occasions to use them, but anyway, same thing does work in those cases. So for example, to store information about people, we could keep a database, a set of 3 tuples, a name, an ID number, and an age. And then everybody that we try to keep track of is associated with an element of D0 cross D1 cross D2. Okay, so we're thinking of these cross products as somehow thinking of these Cartesian products as somehow like a database. It's where you store information. You have something in the first place, something in the second place, something in the third place. Okay, again, vocabulary, but if we don't have vocabulary, we can't talk sensibly. The power set is the set of all subsets. I find this list easiest to work by starting in the middle. So let's look at the set 0, 1, and I want to write down all subsets of 0, 1. So can you see I wrote down the subset consisting of both numbers, the subset consisting of only the 0, the subset consisting of only the 1, and the empty subset. Next, 0, 1, 2. I got to write down all subsets, and when it gets to a certain size, and for me 3 is a big enough size. When it gets to a certain size, if you aren't systematic about it, then you're in some trouble. So here I wrote down all the size 3s, all the size 2s, and then all the size 1s, and then like that. Oh, I left one out. No, there's the 2. Okay. Okay, so all the size. So 0, 1, 2, 0, 2, 1, 2, and 0, 1. 2, 1, 0, and empty. So that's all the subsets of 0, 1, 2. Okay, now going up to the more sort of, sometimes the simpler cases are harder. So just a 0. So you could have just a 0, or you could have the empty set. What about the empty set? There aren't any subsets of the empty set, so there you go. So I'm missing curly brackets. There's supposed to be a set. There's supposed to be a set of curly brackets there. Typo. So it's supposed to be a set of curly brackets there, indicating that the only subset of the empty set is itself, and then that collection should contain just the empty set. I'm sorry. I'll fix that when I upload the slides. Please note that the cardinality of the power set is 2 to the cardinality of A. So here there are 8 things that are subsets of this size 3. There are 4 things that are subsets of this size 2. There are 2 things that are subsets of this size 1. And I'm sorry, I'm missing a pair of curly braces there. It's supposed to be that there is 1 thing that is a subset of this size 0, 2 to the 1. Excuse me, 2 to the 0 is 1. So just a typo, that's all. Okay, so rounding up toward the end here. Set identities. So we can write down some equations using the operations that we did earlier, and that those set equations make up the subject called Boolean algebra. We won't worry too much about these equations, just simpler ones. And just as an example, intersection distributes over union in this way. So A intersect B union C is A intersect B union with A intersect C, and you can learn all kinds of complicated set identities. We won't worry too much about them, but some of the easier ones we'll worry about. We often prove the set identities by showing mutual inclusion. That is to say, if you wanted to show this set identity, we will show 2 different things. We'll show first that A intersect B union C is a subset of the right-hand side. And then we'll show that A intersect B union C is a superset of the right-hand side. That's mutual inclusion. We show that the left is a subset of the right, and the right is a subset of the left. In order to show things by mutual inclusion, the easiest thing to do is to assume you have a generic element x in capital X, and from that assumption show that y is in capital Y. So you would have a paragraph where you suppose x is an element of A intersect B union C, and then you do a little work, and you go on to show that x is therefore an element of A intersect B union with A intersect C. End of paragraph. New paragraph, you show that y is an element of A intersect B union A intersect C, and then do some work, and go on to conclude that y is therefore an element of A intersect B union C. That's called the generic element argument. Okay, we'll practice some of those in class. Just as a comment here, I wanted to make a comment or two. So the sets are typically used as a foundation for mathematics. So in some sense, strictly speaking, everything that a person does in mathematics can be expressed in the language of sets. It was Cantor in sort of 1888 that started that ball rolling, and everything that you do in some sense can be expressed using sets. It's an active branch of mathematics with all kinds of research topics that range from the structure of the real line to the consistency of numbers that are very, very large. And one more point that will arise, that we'll have occasion to talk about a little bit in 208, the axiom of choice. When you write down the rules for mathematics, it turns out that one of the rules is a little bit controversial, and that's this rule here, the axiom of choice. Given a collection of non-empty sets, is the Cartesian product of that collection non-empty? Now you think, well, why can't you have something from the first, something from the second, something from the third? It turns out to be a little tricky to reason through that, because which thing from the first, which thing from the second? If there's infinitely many sets, capital S, then it's not clear how you pick things, one from each of infinitely many choices. That's not perfectly clear. So it doesn't follow from the usual axiom for set theories. You have to take it as a separate axiom. Most mathematicians consider it intuitively clear. However, it implies some results that many people consider puzzling. I'll just mention one, and this is not for homework or anything, so just to give a person some idea. The Banach-Tarski paradox, we have a couple of very nice books about the Banach-Tarski paradox in the library. If you give me two solid objects, for example, a sphere of radius 1 and radius 2, then I can decompose, to be specific, I'll take the sphere of radius 1, I'll decompose it into a finite number of non-overlapping pieces. So I cut up this sphere of radius 1 into a finite number of non-overlapping pieces. I think 7 is a good enough number. 7 non-overlapping pieces. And then you can move them around in space, and when you reassemble, they've become a sphere of radius 2. So that strikes people as not possible in the real world. So that strikes people that the axiom of choice, which implies you can do this, is problematic. So there's some small controversy about some of the things in set theory. I don't want a person to leave this section with some idea that this stuff is all very dull. We did this in 7th grade and it's all very easy. In fact, there's all kinds of interesting stuff. But for us, we're mostly interested in getting to the kinds of mathematics that you do in computers, and this is an aside. This is not the kind of mathematics that you do in computers typically. Okay, anyway, so that's it for today. Very nice.